My name is Andre Horvat, and today I would like to say a few words on fire dynamics and its simulation using computational fluid dynamics, or CFD as it is popularly called. The lecture with the title Fire Dynamics, Comparative Analysis of CFD Simulation Tools and Their Utilization was initially presented at the seminar CFD and Evacuation in Built Environment in Tel Aviv in December 2015. The subject is organized in 6 sections. In the introduction, I will look at what is computational fluid dynamics, what are the drivers behind its development and benefits of its use. Modeling principles associated with fire dynamics will be reviewed in the next section. Zone models will be briefly mentioned. More time will be spent to explain origins of spatial discretization and development of field models. In the validation and verification section, I will quickly present quality criteria associated with CFD simulations and specifically with fire modeling. Generic best practice principle will be also discussed. We will review different aspects of general and specialized CFD simulation tools, including geometry resolution, grid generation techniques, turbulence, reaction, and thermal radiation modeling. A comparative analysis of Fire Dynamic Simulator (FDS) and ANSYS CFD codes will be presented using few fire simulation examples. At the end, I will summarize highlights of the presentation. Introduction. At the beginning, it is important to answer the question, what is CFD? CFD, that stands for Computational Fluid Dynamics, is a field, discipline, area of simulation analysis where a practitioner recreates and visualizes the process based on fundamental mathematical relations of physics, chemistry, biology, economics, social interaction, etc. I intentionally avoided limiting the area of interest to fluids, as other transport phenomena, most notably heat and mass transfer, are often included. Simulation process is used increasingly as a performance-based design tool to support engineering analysis and to complement experimental and testing programs, or even to substitute them. The reasons for this are mostly economic, as the simulation techniques offer greater flexibility in managing testing environment, a faster turnaround time, more comprehensive post-processing options, and lower costs. In some cases, safety considerations make physical testing impractical altogether. Such cases can be found in fire engineering, nuclear safety, and space equipment design, to name just a few. Therefore, an overall trend in engineering process can be recognized. Design by experiment or by test is being substituted with design by simulation. Despite all these advantages, it is important to recognize that the simulation process is fundamentally different from physical experimentation and testing. In the world of numerical simulation, most of the effort is focused on recreating reality in a digital environment. Once the created virtual reality is representative of the analyzed environment, capturing relevant data is often much simpler than during physical testing. Initially, reality of interest has to be described using mathematical formalism. The question then arises how well the mathematical abstraction corresponds and confirms reality. Such mathematical model has to be translated into a computer model that allows computational execution and simulation of defined real-world scenarios. Verification activities are required to confirm that the computational implementation accurately represents the mathematical conceptual description. In addition, validation looks at the degree to which the computational model is an accurate representation of the real world from the perspective of the intended use of the model. These assessment activities shall be an integral part of the simulation quality assurance process. More on the subject will be said later. Fire dynamics and modeling principles. We have to recognize that fire is a complex phenomenon. To borrow from Wikipedia, fire is a rapid oxidation of a material in the exothermic chemical process of combustion, releasing heat, light, and various reaction products. It involves chemical reactions that are defined by reaction mechanisms and lead to change in composition, release of heat, and the associated convection, conduction, and radiation mechanisms, as well as external factors such as supply of fuel and oxidizer, convective parameters such as wind direction and strength, radiation emissivity and absorptivity, thermal far field conditions, and so on, to name just a few. Due to complexity, analytical tools are of limited applicability. The required simplification would be too large for such analytical results to have a practical value. The solution is in space discretization. This means breaking space onto discrete volumes where thermodynamic conditions can be considered constant. The exchange of mass and energy between these volumes is then governed by the difference in temperature, pressure, velocity, and composition. These relationships really define the model complexity and do require a certain level of empiricism. In general, larger are the control volumes for which conservation equations are solved, larger is the degree of empiricism required. On the left side of the block diagram, we have zone and lump parameter models where the control volumes are the largest and the degree of empiricism is high. It has to be recognized that it is also hard to generalize such models for different fire situations. The other extreme are models based on Boltzmann transport equations and molecular dynamics, which at present are rarely used in engineering practice, mostly due to their high computational costs. Although such models utilize less empirical findings, their experimental validation becomes more problematic due to small scale of model phenomena. Computational fluid dynamics occupies the middle. It is important to add that computational fluid dynamics, or CFD, is really a very flexible computational method that is able to cover a large range of different scales, from a micron to a meter, from a millisecond to an hour, and beyond. Zone models are the simplest modeling representation of fire. Their theoretical base is conservation of mass and energy in a space separated onto zones. Such models take into account released heat due to combustion of flammable materials, buoyant flow as a consequence of fire, mass flow, smoke dynamics, and gas temperature. In general, we can identify 1 and 2 zone models. In front of us is a typical arrangement of a 2-zone model. The space is separated onto a hot upper zone and a cold lower zone. The conditions, that is temperature, density, and pressure, are treated as uniform in each zone. For the fire itself and for 2 zones, a set of mass and energy conservation equations is defined. They relate conditions between the zones and allow simulation of different fire scenarios. Such zone models are extremely fast, but they are limited to the geometrical arrangements that they can describe. Also, they cannot capture a detailed picture of the flow and thermal conditions. Further domain discretization leads to so-called field or CFD models. This also allows us to reduce the level of empiricism and instead rely on more elementary first principle physics. Overall, this leads to more accurate simulation results. At this point, it is worth revisiting the question, what is computational fluid dynamics? It is a group of methods and algorithms to solve discretized fluid flow and heat transfer equation, as well as their derivations. Validation and verification. As the complexity of models increase, we have to pose the following questions. How do we know that the models give correct and accurate results? Just relying on the software capabilities is clearly not sufficient. All sorts of things can go wrong, even if the software is perfectly adequate for the intended use. For a start, we can formulate a few very generic guidelines, such as simulated problem needs to be well defined. Analysis objectives must be understood. Performance parameters need to be determined, and quality acceptance criteria such as modeling uncertainty, numerical errors, results variability, and sensitivity have to be agreed. We can approach quality control of simulation analyses through validation and verification cases. These have to be geometrically simple. We do not want to spend too much time preparing the cases. They have to contain the representative and predominant physics. If the phenomenon cannot be isolated to the satisfactory degree, its main parameters will be hard to establish and measure. We need to have available and suitable experimental or theoretical data. It is important to emphasize that such cases not only test the methodology and toolset, that is, software, but also the practitioner. Although some of validation and verification activities are generic and can be conducted independently from the project work, the experience showed that a part will always be highly focused on a specific problem, that is, specific project. We can be now more specific and ask, what are typical performance parameters in fire modeling? They may be case dependent, but in general, conservation of mass, momentum, and energy has to hold. Therefore, we can state that adiabatic temperature of combustion shall not be exceeded, release energy shall not exceed the net reaction heat, flame speed should not exceed experimentally published values, composition change shall match the reaction rate over the simulated time interval, far-field heat flux shall not exceed heat flux associated with fire irradiation, different correlations associated with atmospheric dispersion and heat transfer shall hold, and we have to recognize that supersonic flow speeds are rarely associated with fires, especially in an open environment. CFD analysis codes. From engineering perspective, fire dynamics is essentially a fluid flow and heat transfer problem. Therefore, a number of general as well as more specialized CFD packages are used in simulation and analysis of fire-related scenarios. Let's mention just a few general CFD packages that are used most frequently. These are ANSYS-CFX, Fluent, StarCD, Numeka, COMSOL, OpenFOAM, etc. On the other hand, Fire Dynamic Simulator, or FDS, Flux, KFX, SOFI, and SmartFire were developed specifically for fire and explosion modeling. It is important to recognize that there are significant differences between these tools in their simulation approach, physics and chemistry models, user-friendliness, support, and business framework. All this matters in selecting the right tool, and it should not be underestimated. First area of differentiation that we will look at is geometry resolution. A practitioner needs to understand which geometrical features to resolve and which to represent through subgrid models and which to completely exclude. The top left figure shows a case where the numerical model fully resolved the geometry. This allows capturing the wall boundary layer effects where most of the momentum and heat transfer takes place. The figure below illustrates the immerse solid method that simply blocks the flow in the cells where the solid body appears. In most cases, such simulation domain crudely follows contours of the solid object, making the resolution of the boundary layer impossible. In cases with particularly complex geometrical arrangements, an example on the right shows a process plant, subgrid modeling is used to approximate momentum and heat exchange between objects that were too small to be resolved by the numerical grid and large-scale flow behavior. There is a whole hierarchy of different subgrid models, and they vastly simplify preparation of CFD simulation models. Nevertheless, they all rely on significant amount of empiricism, which may lead to wrong conclusions. Grid types and generation methods are another important subject. There are almost as many ways of generating numerical grid as CFD packages. Most of commercial CFD packages offer multiple methods, which clearly shows that there is no best way, or that each method offers its advantages and disadvantages. In general, a numerical grid can be structured, as in FDS or KFX, or unstructured, as in ANSYS or STAR-CD. Structured numerical grids offer much faster simulations and less complexity in the implementation of CFD models, but on the other hand, fundamentally less flexibility in modeling geometrically complex forms. They can be recognized by their Cartesian elements, sometimes in their body-fitted forms, whereas the unstructured grids may consist of hexahedral, tetrahedral, prismatic, or even polyhedral elements. Different hybrid variations can also be found. More recently, a group of grid overlapping methods appeared. They are often referred as overset or nested grid approach. They allow the use of different grid types in the same simulation domain. These grids are not embedded but overlaid, with the flow field being interpolated between different grid levels. Although not widely applied in the CFD community, such techniques offer the maximum degree of flexibility. It is important to emphasize that numerical grid is the critical component of the CFD simulation process. On one side, it defines the quality of numerical results, and on the other, it provides foundation for any software development. Another very important aspect of flow physics modeling is turbulence. In general, we distinguish algebraic turbulence mixing models, two-equation turbulence models, Reynolds stress modeling, large eddy simulation models, and the different hybrid combinations. They all have their advantages and of course disadvantages that deserve attention and must be taken into account. Figures in front of us show a simulation of a gravity current in a shipping container where a cold stream moves inward and a plume of hot gases moves outward. The results on the left were obtained with a transient Reynolds average Navier-Stokes or Rans model, and the results on the right with the large eddy simulation or LES turbulence model. I promise I'll try to keep the use of acronyms to a minimum. Now, even an immediate visual comparison convinces us that the LES model results reveal more flow details than the results obtained with the Rans model, and as such should be more accurate. But LES modeling results are notoriously sensitive to the density of the numerical grid. Using LES models on a numerical grid that is too coarse may lead to wrong results, especially if the combustion rate depends on the level of turbulence, which is mostly the case in the environmental flows. The figure shows the energy cascade of turbulence eddies. The turbulence eddies should dissipate as we move toward larger wave numbers and therefore disappear. If the numerical grid is too coarse, smaller eddies will be overrepresented. This is visible in the diagram in front of us, where the LES results are presented for different grid resolutions. In fire modeling, LES models applied to a coarse numerical grid will lead to increased mixing, further promoting combustion. It has to be said that Rand's turbulence models are much more robust and do require a less dense numerical grid. Let's move forward to fire modeling. Fire itself can be described using discrete heat sources. In such case, information on chemical composition is lost, and thermal loading is usually underestimated. Theoretically more demanding, and from the modeling point of view fundamentally more complex, is the representation of fire with the associated chemical reaction. This requires solving transport equations for composition, using chemical balance equations for conversion of chemical species, and reaction rate model, which tells us how fast is the reaction. Different reaction models, such as the eddy dissipation model, flamelet model, finite chemistry model, burning velocity, or mixes burn model, to name just a few, correspond to specific chemical and flow conditions. A CFD practitioner should understand their applicability and especially their limitations. The diagram shows how the composition and temperature vary across the fire front in premix fire conditions, where fuel and oxidizer are on one side of the reaction zone and the combustion products at significantly higher temperature on the other. As you can see, the reaction zone is a very thin layer with an approximate thickness of 0.01 mm. Adjacent to the reaction zone is the preheating layer, where the reactants are preheated to the combustible temperatures. Due to its limited thickness, the combustion reaction very much depends on flow conditions, with limited speed and strain to sustain it. First area of differentiation that we will look at is geometry resolution. A practitioner needs to understand which geometrical features to resolve and which to represent through subgrid models, and which to completely exclude. The top left figure shows a case where the numerical model fully resolved the geometry. This allows capturing the wall boundary layer effects where most of the momentum and heat transfer takes place. The figure below illustrates the immerse solid method that simply blocks the flow in the cells where the solid body appears. In most cases, such simulation domain crudely follows contours of the solid object, making the resolution of the boundary layer impossible. In cases with particular In fire simulations, thermal radiation should not be neglected. The simplest approach that I have observed is to reduce the heat release rate of fire. Initially, FDS utilized such crude method, where the fire heat release rate was reduced for 35%. Modeling of thermal radiation means solving the transport equation for radiation intensity. We can see that change of intensity along the optical path or track depends on absorption and scattering, local emissions, and inscattering. In optically thick environments, a simple diffusion equation will yield reasonable results, whereas in optically thin environments, the radiation transport equation needs to be solved for a range of optical tracks. The procedure is fundamentally more challenging and computationally demanding. For that reason, modeling of thermal radiation is probably the weakest feature in many CFD packages used in fire simulations. The animation shows a flashover experiment where wood pieces are ignited due to thermal radiation. Due to symmetry, only one half of the experimental setup was modeled. It consists of a propane burner under the metal hood, which helps to create a stable hot layer of combustion products. Below the hot layer, 3 pieces of wood were located away from the central burner. Time to ignition of these solid fuel targets was measured. Simulation results were then compared with experimental values. When all the solid fuel is consumed, the fires extinguish. When choosing CFD analysis code, two additional aspects need to be considered. First is user support. Namely, an adequate support of CFD practitioner is essential to achieve high productivity and to utilize the software to its full capabilities. The other aspect is the software provider's business model, and you might ask yourself why. The software can be provided as an open source code for a one-off or an annual license fee, or can be funded through a governmental agency. What we should not forget is that the development cycles of engineering software are short, 6 to 12 months between major releases. The software is constantly improved and therefore maintenance is required. All this requires constant effort, which means funding. Comparative analysis. Next, the presentation focuses on a comparative analysis of fire dynamic simulator, FDS, and ANSYS simulation tools. The analysis was a part of a study conducted by ANSYS to evaluate performance of their simulation tools. 3 different fire scenarios were studied. Fire in an enclosure conducted by Ulster University, fire in a tunnel under natural ventilation conditions, known as the Memorial Tunnel Experiments, fire at the King's Cross Underground train station. These cases were selected due to their transient behavior, importance of convective and radiative heat transfer across the walls, or in the last case, complex geometry. The following toolset was used for preparing the simulation models and for conducting the CFD simulations. Fire Dynamic Simulator, FDS, which is computational fluid dynamics software for simulation of fire-driven fluid flow. SmokeView, a visualization program that is used to display the output of the FDS and CFAS simulations, and PyroSim, a commercial graphical preprocessor from Thunderhead Engineering. The FDS and SmokeView applications have been developed by the National Institute of Standards and Technology, NIST, of the United States Department of Commerce, in cooperation with VTT Technical Research Center of Finland. The software solves numerically a form of the Navier-Stokes equations that is appropriate for low-speed, thermally driven flows with an emphasis on smoke and heat transport from fires. In addition, it is also worth mentioning other simulation packages related to FDS, for example, Blender FDS, FDS Designer, which are currently under development. The fire experiment in enclosure that will be discussed here was performed at the University of Ulster. The enclosure, representative of a scaled-down ISO container, was 80 cm long, 80 cm high, and 120 cm wide. A sand burner with a prescribed methanol mass flow rate was placed in a corner of the enclosure. The whole experiment lasted for 650 seconds. The performed CFD analysis included a full combustion model, radiation heat transfer, and heat transfer across the walls. Temperatures were monitored at 9 vertical locations at the wall opposite the burner. In addition, heat fluxes were also measured at 25 different locations across the entire wall. left are the temperature readings from the thermocouples 2 and 8. The thermocouple 2 was located in the hot layer and the thermocouple 8 in the cold layer. Similarly, the heat flux gauge readings are on the right. The heat flux gauge 11 was located in the hot layer and the heat flux gauge 15 in the cold layer. The experimental data are marked with black dots. The CFD results obtained with FDS are red and those obtained with NCCFX are blue. For both cases, identical structured numerical grid was used. For comparison, a black line shows the CFD results computed with NCCFX on a numerical grid refined near the wall. All the experimental data and the CFD results confirm significantly higher temperatures in the upper hot layer. They are 200 degrees Celsius higher than in the lower cold layer. As a result, the heat flux to the wall also doubles. A comparison of CFD analysis results showed that both codes, FDS and CFX, accurately predict the near-wall temperature variation in the upper hot layer. On the other hand, in the cold layer, where thermal radiation is the dominant mechanism, FDS significantly underpredicts the temperatures. Prediction of heat flux, that is convective heat flux and irradiation, is a hard task for both codes, and only an additional refinement of the near-wall grid improves the prediction. It has to be recognized that such localized near-wall grid refinement is only possible when the unstructured grid generation method is used. Relying on a structured grid approach to resolve near-wall effects would require a much larger numerical grid and consequently much larger computing resources. Another well-documented experimental case that was used for CFD code comparison is the Memorial Tunnel experiment. This was a full-scale fire experiment conducted in West Virginia, United States in 1995. A 50 megawatt fire was set in an 853 meter long road tunnel with a cross-sectional area of 59.6 square meters and an inclination of 3.2% from south to north. In the CFD model, a propane mass inflow of an equivalent fire heat release rate was imposed at the location of fire. A full combustion model was used together with the radiation heat transfer. To model heat exchange between the airflow and the tunnel wall, a heat transfer coefficient was prescribed at the wall. Measured velocity profiles and temperature readings were used for comparison with the CFD results. FDS uses a structured numerical grid. As figure shows, the simulation domain needs to be defined as a simple rectangular volume. Non-rectangular, in this case cylindrical shapes, need to be carved out from the initial volume using rectangular blockages. Due to rectangular blockages, curved walls are not smooth and therefore the boundary layer is not approximated. The process of creating blockages quickly becomes too complicated, especially for volumes which are not aligned with marine coordinate axes or have otherwise complex shape. A fair degree of process automatization can be achieved with PyroSim, provided by Thunderhead Engineering. Figures in front of us display a calculated temperature field, 120 seconds since the start of the fire. ANSYS-CFX was used to obtain the simulation results shown in the figure A above, and FDS for the simulation results in the figure B below. In the CFX simulation, the hot upper layer shows a much larger degree of flow instabilities. These are the Kelvin-Helmholtz and the Rayleigh-Taylor instability, which are responsible for a visibly wavy structure of the hot layer. Due to this additional mixing and resistance, the CFX simulation results show slower progress of the hot layer than predicted by the FDS code. If we compare the temperature field cross-sections obtained by both codes, we can observe that the hot layer, as predicted by the CFX code in the figure on the left, is colder and thinner than when calculated by the FDS code in the figure on the right. This is a direct consequence of the additional mixing captured by the CFX code, as well as of the turbulence models utilized to simulate the thermally stratified flow. In the figure below, flow velocities are compared for one of the locations, 12.19 meters south of the fire. In both cases, CFD results do overpredict the flow velocity induced by the fire. Systematically, the FDS results do show a larger discrepancy from the experimental data than the CFX simulation results. Fire on the underground train station in King's Cross in London has been often studied using experimental and CFD simulation techniques. To briefly repeat a few factual information, the King's Cross accident occurred in November 1987. The fire started in an escalator tunnel of an underground station. The affected escalator connects the Piccadilly line tunnel and the ticketing hall. The tunnel is almost 50 meters long and with an inclination of 45 degrees. The fire heat release rate was estimated to be 1.6 megawatts. The CFD analysis was conducted using transient fire modeling simulation, the inert fire model in CFX, and the full combustion model with radiation in FDS simulation. The calculated temperature distribution in the tunnel was used for qualitative comparison of simulation results. Another very important aspect of flow physics modeling is turbulence. In general, we distinguish algebraic turbulence mixing models, two-equation turbulence models, Reynolds stress modeling, large area simulation models, and the different hybrid combinations. They all have their advantages and of course disadvantages that deserve attention and must be taken into account. Figures in front of us show a simulation of a gravity current in a shipping container where a cold stream moves inward and a plume. The figure on the left shows the temperature field calculated with the FDS code, whereas the temperature field on the right was obtained with the NCCFX. The temperature scale in both figures is the same to simplify the comparison. It can be observed that the CFX results show a more pronounced trench effect. Fire is aligned with the escalator much longer. This indicates much stronger entrainment of the surrounding air than in the FDS results. Although both models calculate a similar maximum temperature, its extent and distribution are different. The FDS results show a very limited area that is affected by the fire, with the temperature reaching its maximum near the tunnel ceiling. On the other hand, the CFX results indicate that much larger area in the escalator itself is exposed to high temperatures. These differences are important, as they directly relate to risk of injury and loss of life. We can approach quality control of simulation analyses through validation and verification cases. These have to be geometrically simple. We do not want to spend too much time preparing the cases. They have to contain the representative and predominant physics. If the phenomenon cannot be isolated to the satisfactory degree, its main parameters will be hard to establish and measure. We need to have available. It was established that in the region where thermal radiation is a dominant heat transfer mechanism, FDS significantly underpredicts temperature. Heat fluxes on the walls too are in general underpredicted by the FDS. This difference is small in the convection-dominated region, but becomes larger, up to 40%, where thermal radiation is important. Besides possible modeling shortcomings of thermal radiation heat transfer, there are also more serious accuracy limitations related to grid resolution of the near wall layer. That was briefly touched upon in the lecture. In the FDS, the only available turbulence model is the Large Eddy Simulation, or LES model, which is not appropriate for the grid resolution outside the inertial subrange of turbulence. As standard, FDS offers the mixing fraction combustion model. The laminar Flamen model is also available, but it is advised to use direct numerical simulation, or DNS, to produce valid results. Solver parameters to control accuracy of the solution are not accessible to a user. Also, tracking the progress of the numerical solution and its residuals is only available in a command line mode. As the rectangular structured mesh cannot describe an arbitrary shape of the simulation domain, FDS uses rectangular blockages to suppress the numerical solution over a certain location. A representation of complex shape with blockages is very time-consuming and often impossible. Pre-processing software Pyrosim from Tinderhand Engineering to a great extent automates the geometry pre-processing and solves the problem. Nevertheless, describing curved surfaces with a rectangular section produces step-like surfaces which often cannot adequately capture boundary effects. Inability to locally refine the numerical grid limits the result's accuracy, as the important local effects such as boundary layer, wall heat transfer, mixing, combustion are underrepresented. It is important to emphasize that development and maintenance of analysis software requires continuous effort and funding. Although capabilities of individual software packages are certainly important, the weakest point remains human factor, that is, analyst. I would like to thank you all for your attention. I hope you found the lecture interesting. For any specific question, please do not hesitate to contact me.